include safe entry and exit procedures to avoid incidents like the one I just told you.
They're not the only way transmission can occur. Dermatitis or other
It never
skin
occurred to me
lesions
that a few
provide-
quarts of oil could contribute to the pollution of our environment.
Great training session. The one thing that we tried to project...
Change an auto head. Go through the shutdown.
30 minutes after this business closed, the discarded contents of an ashtray started a fire in a waste can, which spread to a stack of paper files. Although the fire department is not yet on the scene, this fire is already being fought. This building is equipped with an automatic sprinkler system that began controlling the flames a short time after they appeared. Sprinkler systems such as this one are responsible for saving millions of dollars each year in expensive buildings, equipment, and stock. They're also responsible for preserving jobs and, most importantly, protecting precious lives. As a loss control representative, part of your responsibilities require you to have a basic understanding of sprinkler systems as they relate to risk evaluation. Today, we'll explore the 4 basic types of sprinkler systems, including the factors influencing their design and selection, components common to each of these systems, water supplies and special occupancy conditions, and building features you may encounter. First, let's identify the 4 basic types of sprinkler systems. They are wet pipe, dry pipe, pre-action, and deluge. The most common and economical type of sprinkler system is the wet pipe system. This system employs automatic sprinklers attached to a piping system that contains water under pressure. As soon as a fire causes one or more sprinklers to open, water is immediately discharged. Contrary to popular belief, sprinklers work independently of one another, and only those in the immediate fire area will open to discharge water. The wet pipe system requires an indicating device, which signals when one or more of the automatic sprinklers are activated. 2 methods of indicating water flow are the pressure switch and the water motor gong. Water flow indicators using a vane or paddle and a pressure switch are commonly used on new systems. The vane extends into the waterway sufficiently to be deflected by any movement of water flowing to the general sprinklers. Motion of the vane activates the pressure switch, which causes an alarm signal to be generated. The second method incorporates the alarm check valve. Its identification is usually stamped on the faceplate of the valve. A clapper is positioned inside the valve, which is hinged on one side, to ensure that water flows in only one direction. When this clapper is unseated to permit water flow, it also triggers an alarm device, usually a water motor gong or a pressure switch, that activates an audible or visual alarm. Wet pipe systems are very efficient and prompt because water is in the pipes at all times. If a building is adequately heated, a properly designed wet pipe sprinkler system will provide good fire protection. However, some buildings have small areas that may be subject to freezing conditions, even for short periods of time. If this is the case, an antifreeze solution in a portion of the wet pipe system may be necessary. Because antifreeze solutions are costly and may be difficult to maintain, their use is limited to small, unheated areas. The second type of sprinkler system is the dry pipe system. Unlike the wet pipe system, which contains water, the dry pipe system maintains its piping dry and under pressure. This system employs automatic sprinklers attached to a piping system containing air or nitrogen under pressure. When one or more sprinklers are opened, the pressure is reduced, opening a dry pipe valve, which allows water to enter the piping. The water is discharged upon reaching any open sprinklers. Again, only those sprinklers in the immediate fire area will open. One characteristic of the dry pipe system is a delay in time between the opening of a sprinkler and the discharge of water. This delay allows the fire to grow, and as a result, more sprinklers open. To reduce its reaction time, dry pipe valves are equipped with quick opening devices, such as accelerators and exhausters. Although the two types operate somewhat differently, both rapidly reduce air pressure in the system, minimizing response time. Water flow indicators of the vane or paddle type cannot be used in a dry system because the sudden rush of water is likely to damage the vane and mechanism. As with the wet pipe system, the dry pipe system's water flow indicating devices also include water motor gongs and pressure-activated alarm switches. The water supply pipe below the dry pipe valve contains water at all times and must be properly protected from freezing. When potentially exposed to cold, it must be housed in a well-constructed, lighted, and heated enclosure, allowing ready access to the valve. Dry pipe systems require more maintenance than wet pipe systems, but when properly maintained, can be relied upon to satisfactorily control fires. The third type of system is the pre-action system. Like the dry pipe system, all of the piping in the pre-action system is maintained dry and is therefore appropriate for use in areas subject to freezing temperatures. The major difference between the two systems is that the pre-action valves are designed to open only in response to activation of a fire or smoke detection system. Before water is discharged, both the detection system and an automatic sprinkler must be activated. Fire detection devices used with pre-action systems include the rate of rise type detector, fixed temperature devices, and smoke or combustion products detectors. The primary application of the pre-action system is in those areas where an alarm in advance of the sprinkler operation is desirable, and most importantly, where accidental discharge of water cannot be tolerated, such as a data processing center. Because a fire detection device will increase the cost of a pre-action system, the use of an ordinary dry system may be dictated, unless water damage is of great concern. The fourth type of sprinkler system is the deluge system. Deluge systems are basically the same as pre-action systems in that they operate automatically by a separate fire detection system. However, unlike the other systems we've discussed, which employ closed sprinklers, the deluge system employs open sprinklers. This means that water will be discharged from all sprinklers simultaneously, not just those in the immediate fire area. Deluge systems are suitable for various extra hazard occupancies in which flammable liquids or other hazardous materials are handled or stored, and where there is a possibility of fire flashing ahead of the operation of ordinary automatic sprinklers. Whatever the type of sprinkler system, wet pipe, dry pipe, pre-action, or deluge, certain components are common to each. These components consist of the following: the automatic sprinkler, piping, control valves, and the fire department connection. An automatic sprinkler is essentially a small nozzle. A unique feature of automatic sprinklers is that they are temperature responsive. When the temperature reaches a predetermined level, the sprinklers automatically release a stream of water, distributing it in specified patterns and quantities over designated areas. An automatic sprinkler consists of three parts: the releasing device, the orifice, and the deflector. The discharge of water from an automatic sprinkler is restricted by a cap or valve held tightly against the orifice by a releasing device. One type of releasing device is the fusible link and lever. Two levers are held in place by a two-piece link, which is soldered together. When the ambient air temperature rises to melt the solder, the links separate, and the levers fly apart, allowing water to flow. Another type of releasing device is a frangible or liquid-filled glass bulb. The glass bulb, located between the orifice and deflector, holds back the water. When the air temperature rises, the liquid inside the bulb begins to expand. As the temperature continues to increase, the expanding liquid eventually shatters the bulb, thereby initiating the release of water. Different temperature ratings are achieved by varying the amount of alcohol in the glass bulb. The different ratings are indicated by the color. Other styles of releasing devices include bimetallic discs, chemical pellets, and fusible alloy pellet. The temperature rating of automatic sprinklers is either stamped on the releasing device or deflector, or indicated by the color of the frame, or by liquid color. An intermediate temperature sprinkler will have a rating of 212 degrees Fahrenheit, stamped on the fusible link, and indicated by the white color frame. A high temperature sprinkler has a rating of 286 degrees Fahrenheit, and is also stamped and indicated by a blue color frame. The second part of an automatic sprinkler is the orifice or nozzle. Although the diameter may vary, 1/2 and 17/32 inch are the most frequently encountered sizes. Small orifice sprinklers ranging from 1/4 through 7/16 inches, and large orifice sprinklers with 1/2 inch threaded connections are identified by either a pintle, which extends above the deflector, or by the size stamped on the base or frame of the sprinkler. The third part of an automatic sprinkler is the deflector. Originally, sprinklers were equipped with deflectors that directed about 40% of the water upward. These are known as old-type sprinklers and are generally not recommended for new installation, except in fir vaults and piers. However, they need not be replaced in existing facilities. The modern or standard sprinklers have deflectors designed to break up the solid jets of water into fine droplets, which are dispersed in an even water distribution pattern. Standard sprinklers are designed to be installed and operated in their proper design position, for example, upright and pendant. These sprinklers are stamped with either SSU for spray sprinkler upright or SSP for spray sprinkler pendant. Other types of sprinklers include flush, recessed or concealed, sidewall, corrosion resistant, residential, large drop, and early suppression fast response, ESFR. The spacing between the sprinklers is dictated primarily by the potential hazard that exists at the facility. The area protected by each sprinkler is determined by multiplying the distance between sprinklers on a branch line, or S, by the distance between branch lines, or L. S times L equals the square foot area covered by each sprinkler. For example, if the distance between sprinklers on a branch line is 10 feet, and the distance between branch lines is 12 feet, the protection area covered by one sprinkler head would be 120 square feet. The second component common to all sprinkler systems is the piping. Once water reaches a facility, it is channeled through the underground main, or the lead-in, to a vertical pipe or riser, which extends from floor to roof. The riser is connected to the feed main, which is connected to the cross main. The cross main feeds the branch line, which in turn feeds the automatic sprinklers. The most common type of sprinkler piping is black steel. Other types of piping include copper and plastic. To ensure reasonable distribution of water, pipe schedules were developed to limit the number of sprinklers which may be supplied by various pipe sizes. These schedules have undergone several changes throughout the years. Pipe schedules are usually annotated by the number of sprinklers allowed on each of the 3 initial increases in pipe size. For example, a 2-3-5 system means that 2 heads are allowed to be supplied by the smallest, or 1-inch piping. 3 heads, or 1 additional head, are supplied by the next size, or 1 1/4 inch pipe. And 5 heads, or 2 additional heads, are supplied by a larger size, or 1 1/2 inch pipe. The schedule goes on through 8-inch pipe. NFPA 13, the standard for the installation of automatic sprinkler systems, has pipe schedules for light and ordinary occupancies. NFPA requires systems protecting extra hazard occupancies to be hydraulically calculated. Light hazard occupancies include those having conditions similar to residential dwellings and churches, while extra hazard occupancies include those having conditions similar to flammable liquids spraying and dipping. Today, the most common method of designing sprinkler systems is by means of hydraulic calculations. In hydraulically designed systems, pipe sizes are selected on a pressure loss basis and chosen in accordance with the characteristics of the available water supply. Hydraulically designed systems are identified on blueprints prepared by the sprinkler contractor. Specifications will indicate the rate or density of water discharged in gallons per minute per square foot over a specified area of operation, as well as the amount of water and pressure necessary to produce this specific density. This information is also located on a placard or nameplate attached to the system riser. In order to properly evaluate a hydraulically designed system, this information must be included in your report. If you are unsure what information to include, it is best to copy down everything on the placard, including the name, address, and the telephone number of the sprinkler contractor. The third component of a sprinkler system is the control valve. All automatic sprinkler systems are required to be equipped with a listed indicating sprinkler control valve. You can determine if these valves are open or closed just by looking at them. There are various types of indicating control valves, including the outside stem and yoke valve, or OS&Y, the post indicator valve, or PIV, the post indicator valve assembly, or PIVA, the wall post indicating valve, or WPIV, and the indicating butterfly valve, or IBV. To prevent accidental or deliberate shutoff, it's vital that these valves be secured and supervised in the open position. Non-indicating valves include curb box or roadway valves. These valves are buried and operate with a long-handled key wrench. Since you cannot visually confirm the status of these valves, they should not be used in private fire protection system piping. Generally, these valves are used on underground mains where the public supply connects to the private. They are also used to isolate or shut off fire hydrants. Also, each system will have a check valve. Check valves are one-way valves that prevent stagnant water from circulating back into the drinking water supply. The most common of these are the swing type, wafer type, and reduced pressure zone backflow preventers. The fourth component of the sprinkler system is the fire department connection. This connection allows the fire department to add more pressure to the system to effect better control. Fire department connections must be readily accessible and properly marked. Each connection should be fitted with a check valve, but not a control valve, so that the connection will not be shut off inadvertently. During your survey, it is important to note if the fire department connection is equipped with caps. These caps protect the connection threads from damage and prevent debris from being placed in the waterway. So far, we've identified 4 types of sprinkler systems and the components common to each. But no matter how sophisticated the equipment, it's useless without one vital ingredient: water. Sprinkler systems may be supplied with water from one source or a combination of sources, such as public or municipal systems, suction tanks, gravity tanks, pressure tanks, and fire pumps. Now that all elements of a sprinkler system have been identified, let's consider some special occupancy conditions and building features you may encounter that could affect the operation of the automatic sprinkler system. Certain occupancy conditions require more than ordinary sprinkler protection in order to provide dependable fire extinguishment and control. Special attention should be given to those occupancies which involve large-scale warehousing, flammable and combustible liquids, combustible dust and fibers, chemicals, and explosives. Also be alert to building features, such as unprotected vertical openings, excessively high ceilings, combustible concealed spaces, conditions which shield fires, large undivided areas, and exterior exposures. Additionally, any non-sprinklered areas, obstruction to sprinkler distribution, and inadequate clearance between stock and sprinklers should also be noted. As with all machinery, wear, tear, and age can contribute to serious operational problems. Examine sprinkler heads and pipes for signs of corrosion. Any sprinkler showing signs of damage or leakage should be replaced. Finally, NFPA 13A, Care and Maintenance of Sprinkler Systems, recommends testing representative samples of all sprinklers 50 years old and above at 10-year intervals, and replacing sprinklers manufactured before 1920. We've presented you with a great deal of information today, so let's take a few moments to review. First, we identified 4 types of sprinkler systems: wet pipe, dry pipe, pre-action, and deluge. Remember, only the deluge system employs open sprinklers. Next, we discussed the various components common to each system. These include the automatic sprinkler, piping, control valves, and the fire department connection. We also listed various sources of water supplies for automatic sprinkler systems. And finally, we explored some special occupancy conditions and building features you may encounter during your survey, which could affect the operation of the automatic sprinkler system. If you require additional information regarding automatic sprinkler system identification, contact your regional property specialist or home office loss control. Automatic sprinkler systems have been a factor in the evolution of modern industry, providing protection for extensive properties, hazardous equipment and processes, and high-value materials stored within single buildings. And they're a key factor in our job of loss control.